3i Atlas is racing toward Jupiter with precision that shouldn't exist in nature. Right now, at this very moment, a comet from beyond our solar system is on a trajectory so exact, so mathematically perfect, that it will arrive at Jupiter's gravitational boundary. Not close to it, not near it, but exactly at the precise distance where Jupiter's gravity takes control, with an accuracy that defies the randomness we expect from cosmic wanderers. This isn't speculation, this is happening, and what makes it impossible to ignore is this: the object changed its path after it passed the Sun, and that course correction aimed it directly at Jupiter's Hill radius, with a precision measured in tens of thousands of kilometers out of distances spanning tens of millions. Think about that. An object from interstellar space, travelling for potentially thousands of years, gets close to our Sun, experiences some kind of outgassing event that alters its trajectory, and somehow ends up targeting the exact gravitational threshold of the largest planet in our solar system. The odds of this happening by pure chance are staggering. 3i Atlas! You might have heard about it when astronomers first detected it entering our solar system. It made headlines because it was only the third confirmed interstellar visitor we've ever tracked. A genuine interloper from another star system passing through our cosmic neighbourhood. But what happened after it swung around the Sun in late October is what has some scientists quietly troubled and others openly fascinated. Because 3i Atlas didn't just continue on some random exit trajectory out of the solar system like most comets would, it adjusted its course, and that adjustment, measured and confirmed by multiple observatories, has set it on a path that will bring it face to face with Jupiter in March of next year, specifically on March 16th, at a distance that matches Jupiter's Hill radius to within a fraction of a percent. Let me put that in perspective for you. Jupiter's Hill radius, the distance at which Jupiter's gravity becomes the dominant force on an object rather than the Sun's gravity, is approximately 53.5 million kilometers. When 3i Atlas reaches its closest approach to Jupiter next March, calculations show it will pass at 3.4 million kilometers. That's a difference of less than 100,000 kilometers. In cosmic terms, where we're dealing with planetary distances and gravitational fields that extend for millions of miles, that's essentially a direct hit on an invisible target. It's like throwing a dart from across a football field while blindfolded and landing it in the bullseye. Except the dart travelled from another star system and corrected its own flight path mid-journey. Now, I know what you're thinking. Comets change course all the time, right? They outgaze as they heat up near the Sun, releasing jets of material that act like tiny rocket thrusters, pushing them in different directions. This is well-documented physics. We've seen it happen with dozens of comets. But here's where 3i Atlas becomes genuinely strange. The amount of outgassing detected, the timing of that outgassing event, and the resulting trajectory shift all combined in exactly the way needed to redirect this interstellar visitor toward Jupiter's gravitational boundary with stunning accuracy. And when I say exactly, I mean the margin of error here is so small that some researchers have started asking uncomfortable questions about whether we're looking at a natural phenomenon or something else entirely. Stay with me, because in the next minutes we're going to explore what's really happening with 3i Atlas, what it means when an interstellar object reaches Jupiter's Hill radius, what scientists observed during that October transformation near the Sun, and why this encounter in March could answer questions we've been asking since we first discovered objects from beyond our solar system are passing through our neighbourhood. We're going to separate what we know for certain from what remains mysterious. We're going to look at the data, the theories, and what happens next when spacecraft near Jupiter turn their instruments toward this visitor and record whatever unfolds. Because here's the thing that matters most. We're about to witness something unprecedented. An interstellar comet, an object that formed around another star possibly billions of years ago, is going to interact with Jupiter's massive gravitational field in a way that will either demonstrate remarkable natural physics or reveal something we don't yet understand about how these objects behave. And unlike previous interstellar visitors that caught us by surprise and left before we could study them properly, this time we have spacecraft in position. We have telescopes trained on the approach. We have months of preparation time. We're going to see exactly what happens when 3i Atlas reaches that boundary on March 16th. Some scientists are approaching this with measured curiosity, treating it as an excellent opportunity to study gravitational perturbation effects on an interstellar object. Others, including at least one prominent Harvard astrophysicist, have suggested publicly that the precision involved warrants consideration of non-natural explanations. And yes, I know how that sounds. I know the baggage that comes with even mentioning such possibilities, but the mathematics here are genuinely unusual. The trajectory is genuinely precise, and the questions being raised aren't coming from fringe theorists or conspiracy channels. They're coming from published researchers looking at the same data everyone else can access. So what's really going on with 3i Atlas? Is this an extraordinary cosmic coincidence, a demonstration of how complex gravitational interactions can produce seemingly impossible outcomes through entirely natural means? Or are we missing something important about how interstellar objects behave when they enter planetary systems? Could there be physical mechanisms we don't fully understand that cause certain trajectories to naturally gravitate toward these gravitational boundaries? Or, and this is where the conversation becomes genuinely controversial, could an object from beyond our solar system demonstrate properties that challenge our assumptions about what's natural and what's not? These aren't easy questions. They don't have simple answers, and anyone who claims absolute certainty about what we're witnessing with 3i Atlas is either not looking at the full picture or is more confident than the data warrants. What we have right now is an anomaly, a genuine, measurable, documented anomaly in the trajectory of an interstellar visitor. An anomaly that will either be explained by physics we already understand once we gather more data, or will require us to expand our understanding of what's possible. And this is why you need to pay attention to what happens in March. Because whatever we observe when 3i Atlas reaches Jupiter, whether it's perturbed into a new orbit, whether it maintains its trajectory, whether we detect any unusual characteristics in its composition or behaviour, will give us answers. Real answers, not speculation. Data that will either confirm the natural explanation or deepen the mystery even further. We're 4 months away from one of the most scientifically significant close encounters between an interstellar object and a major planet that humanity has ever had the technology to observe properly. So here's what I want you to do. If you're as fascinated by this as I am, if the precision of this trajectory makes you wonder what we're really looking at, hit that like button right now. And drop a comment telling me what you think is happening here. Do you believe this is natural physics producing an extraordinary coincidence? Do you think there's something about interstellar objects we haven't discovered yet that explains this precision? Or do you lean toward the more controversial interpretations that some researchers have proposed? I genuinely want to know what you think, because this is the kind of mystery that deserves serious conversation, not knee-jerk dismissals or uncritical sensationalism. But before we can intelligently discuss what might be happening, we need to understand what Jupiter's Hill radius actually means, and why reaching this specific distance matters so much. Because without that foundation, the significance of 3i Atlas's trajectory will remain abstract. So let's start there. With Jupiter itself and the invisible sphere of gravitational dominance that surrounds it. Jupiter isn't just the largest planet in our solar system, it's the gravitational giant that shapes everything around it. The massive presence that has influenced the architecture of our entire planetary neighbourhood for billions of years. When we talk about Jupiter, we're talking about a world so enormous that you could fit over 1,300 Earths inside its volume. But size isn't what makes Jupiter truly remarkable from a gravitational perspective. What matters is how that mass creates an invisible sphere of influence that extends millions of kilometres into space, a region where Jupiter's gravity becomes more important than the Sun's gravity for any object passing through. This region has a name, the Hill radius. And understanding what this means is absolutely essential to grasping why 3i Atlas's trajectory is so unusual. Imagine you're standing on Earth and the Sun's gravity is pulling you one direction, while Earth's gravity pulls you the other. At the surface, Earth wins easily, but if you move far enough away from Earth, eventually the Sun's gravity becomes stronger. There's a boundary out there, a distance where the gravitational influence transitions from Earth-dominant to Sun-dominant. That boundary exists around every celestial body in the solar system, and its size depends on the object's mass and its distance from the Sun. For Jupiter, that boundary is enormous. Because Jupiter is so massive, more massive than all the other planets combined, and because it orbits far enough from the Sun that solar gravity has weakened considerably at that distance, Jupiter's gravitational domain extends approximately 53.5 million kilometres from its centre. To put that in perspective, that's more than a third of the distance from the Sun to Earth. Jupiter's Hill radius is so large that it encompasses an absolutely vast volume of space where Jupiter, not the Sun, controls the motion of objects. Why does this matter? Because when any object, a comet, an asteroid, a spacecraft, or in this case an interstellar visitor, crosses into Jupiter's Hill radius, its fate changes. The object's trajectory is no longer determined primarily by the Sun's gravity. Jupiter takes over. The object can be captured into orbit around Jupiter. It can be accelerated, flung into a completely different trajectory, sent careening toward the inner solar system, or ejected from the solar system entirely. Jupiter's Hill radius is a gravitational watershed, a point of no return in many cases, where the rules governing an object's motion fundamentally shift. This is why Jupiter is often called the solar system's guardian. Its immense Hill radius and powerful gravity have intercepted countless comets and asteroids over billions of years that might otherwise have made their way into the inner solar system where Earth orbits. Jupiter has taken hits that we didn't have to take. It's absorbed impacts, captured objects, and deflected potential threats. The famous Shoemaker-Levy 9 comet that broke apart and slammed into Jupiter back in the 90s is a perfect example. That comet crossed Jupiter's Hill radius, was captured by Jupiter's gravity, was torn apart by tidal forces, and then collided with Jupiter while the entire world watched through telescopes. It was a spectacular demonstration of what Jupiter's gravitational dominance actually means in practical terms. But Jupiter's influence isn't just destructive, it's also sculpted the solar system's structure in profound ways. The asteroid belt between Mars and Jupiter exists largely because Jupiter's gravity prevented those asteroids from coalescing into a planet. The gaps in Saturn's rings, the orbital resonances that lock certain moons into synchronized patterns, the way comets from the outer solar system get their orbits bent and redirected, all of this stems from Jupiter's gravitational presence. Jupiter is the architect, the enforcer, the dominant force in planetary dynamics beyond the inner rocky worlds. Now, when we talk about an interstellar object approaching Jupiter's Hill radius, we're talking about something genuinely rare. Most comets and asteroids in our solar system have been here for billions of years. They formed here. They've been orbiting the Sun, getting perturbed by planets, settling into stable or unstable orbits through countless interactions over deep time. They're part of the system. But interstellar objects are different. They came from somewhere else. They formed in a different stellar environment, possibly around a star that doesn't even exist anymore. They've been wandering through the galaxy, and they just happen to be passing through our solar system right now. When one of these visitors encounters Jupiter, we're watching two completely separate histories intersect, the history of our solar system and the history of something that came from beyond it. The interesting thing about gravitational boundaries like the Hill radius is that they're not hard barriers. There's no wall out there. An object doesn't hit something solid when it reaches that distance. What happens is more subtle. The gravitational influence gradually transitions, but there is a definable distance where, mathematically, Jupiter's pull equals the Sun's pull as modified by the object's motion. Cross that line moving inward, and Jupiter increasingly dominates. Cross it moving outward, and the Sun reasserts control. It's a threshold, a transition zone, and it's precisely calculable based on Jupiter's mass, the Sun's mass, and the distance between them. So when astronomers noticed that 3I Atlas was going to pass Jupiter at almost exactly this threshold distance, it immediately stood out as unusual. Because space is enormous, the probability of randomly approaching any specific distance from Jupiter is vanishingly small. Think about it this way. If you drew a sphere around Jupiter representing its Hill radius, and then drew spheres at every possible distance from Jupiter, extending out to millions and millions of kilometers, the volume contained in any thin shell at any one distance is just a tiny fraction of all the possible space an object could pass through. The odds of naturally, randomly passing through one specific shell, especially one as significant as the Hill radius, are extraordinarily low. And yet, that's exactly what 3I Atlas is going to do. After travelling through interstellar space for who knows how long, after entering our solar system along some trajectory determined by its origin point, and the gravitational influences it encountered during its journey, after passing close to the Sun and experiencing that outgassing event, it's now on a path that will take it to within a fraction of a percent of Jupiter's exact Hill radius. Not inside the Hill radius where Jupiter would capture or dramatically deflect it. Not way outside the Hill radius where Jupiter's influence would be minimal. Right at the boundary, right at the threshold where Jupiter's gravity transitions from dominant to subordinate. That precision is what has some scientists puzzled. Because in a random universe, where trajectories are determined by initial conditions and gravitational interactions that unfold according to well-understood physics, you don't expect to see this kind of precision unless something specifically caused it. Either the outgassing event that altered 3I Atlas's trajectory happened to occur with exactly the right magnitude and direction to produce this result, which would be an extraordinary coincidence, or something else is going on that we need to understand. This is why the Hill radius matters so much to this story. It's not just an arbitrary distance, it's the boundary that defines Jupiter's gravitational sovereignty. It's the distance at which objects transition from solar control to Jovian control. And 3I Atlas is threading that needle with accuracy that shouldn't occur randomly. So the question we have to ask is, what determined this trajectory? What physical processes, natural or otherwise, resulted in an interstellar comet arriving at Jupiter's doorstep at precisely the distance where the gravitational transition occurs? To answer that question, we need to go back to what happened when 3I Atlas swung around the Sun in October, because that's when everything changed. That's when the trajectory that's now bringing it to Jupiter's Hill radius was established. Late October 2025 marked the most critical moment in 3I Atlas's journey through our solar system. This was perihelion, the point of closest approach to the Sun, when the comet would feel maximum solar heating and when its icy composition would respond most dramatically to that thermal input. Astronomers around the world had their telescopes trained on 3I Atlas during this period, knowing that perihelion passages often produce spectacular changes in cometary behaviour. What they observed exceeded expectations, but not in the way anyone initially anticipated. As 3I Atlas approached the Sun, it began to brighten. This is standard behaviour for comets. As solar radiation heats their surfaces, volatile materials, frozen water, carbon dioxide, methane and other ices, sublimate directly from solid to gas. This outgassing creates the characteristic coma, the glowing cloud of gas and dust that surrounds the comet's nucleus. For 3I Atlas, this process started weeks before perihelion, gradually increasing in intensity as the distance to the Sun decreased. Observatories in both hemispheres tracked the brightening, measured the spectral signatures of the gases being released, and built up a profile of the comet's composition. What became clear quite quickly was that 3I Atlas had a significant volatile content. This wasn't a dead, inert rock drifting through space. It was an active comet with substantial ice reserves that were vigorously outgassing under solar heating. The spectral analysis revealed water vapour, carbon monoxide, and traces of other compounds you'd expect from a comet. Everything looked normal, everything fit the standard model of cometary behaviour. Scientists were documenting an interstellar comet going through the same processes that solar system comets experience, providing valuable comparative data about whether objects from other stellar systems have similar compositions to our local population. But then came the perihelion passage itself, and things started to deviate from predictions. The outgassing intensified dramatically, far more than the pre-perihelion observations had suggested. 3I Atlas produced a burst of material that created a noticeably brighter coma and a more pronounced tail. This kind of outburst isn't unheard of in comets. Sometimes buried pockets of volatile material suddenly get exposed or internal pressure builds up and releases explosively, but the timing and intensity caught researchers' attention. More importantly, the outgassing wasn't symmetrical. Jets of material were being released preferentially from certain areas of the nucleus, creating an uneven thrust effect. This is where the trajectory change originated. When a comet releases gas from its surface, that gas carries momentum. As the gas escapes, it pushes against the nucleus in the opposite direction, creating what scientists call a non-gravitational force. It's essentially a natural rocket engine, albeit a weak and uncontrolled one. For most comets, these forces are small and somewhat random, causing minor perturbations to their orbits that can be measured but don't dramatically alter their paths. For 3I Atlas, however, the non-gravitational acceleration was both significant and, as later analysis would reveal, remarkably well directed. Multiple space agencies and observatories contributed to tracking 3I Atlas through this critical period. NASA's Near-Earth Object Observations Program maintained continuous monitoring. The European Space Agency coordinated observations from ground-based telescopes across Europe. Observatories in Chile, Hawaii, and Australia contributed southern and mid-latitude perspectives. The data they collected was consistent. 3i Atlas was accelerating in a direction that wasn't purely determined by the sun's gravity. Something was pushing it, and that something was its own outgassing activity. Now, here's where the story gets interesting. As the weeks after Perihelion passed, and 3i Atlas moved away from the sun, astronomers began calculating its new trajectory based on the observed position and velocity changes. They used sophisticated orbital mechanics software, the same tools that track asteroids and predict their future positions. They input the mass estimates for 3i Atlas, the observed non-gravitational acceleration, the gravitational influences of all the major planets, and everything else needed to project where the comet would go over the coming months and years. The results showed something unexpected. Before Perihelion, 3i Atlas was on a hyperbolic trajectory that would have taken it past the sun and back out into interstellar space along a path that wouldn't have brought it particularly close to any major planet. It would have been a brief visitor, swinging through the inner solar system and departing without any significant planetary encounters. But after Perihelion, after the outgassing event altered its velocity, the new trajectory showed a close approach to Jupiter, not a random distance, not a grazing encounter or a passage at some arbitrary separation, a close approach that would occur right at Jupiter's Hill radius. The precision of this emerged gradually as more data came in, and trajectory calculations became more refined. Initial estimates showed Jupiter as being somewhere along 3i Atlas's path, but the exact closest approach distance had substantial uncertainty. As weeks of additional observations accumulated, as astronomers measured 3i Atlas's position with greater accuracy, as the orbital calculations incorporated more data points, the uncertainty bars narrowed. And they narrowed onto a very specific number, 53.4 million kilometers. The match to Jupiter's Hill radius of 53.5 million kilometers became undeniable. This is where scientists started paying very close attention. Because trajectory changes from outgassing are common, but trajectory changes that target specific destinations with precision are not. The outgassing would have needed to occur with a very particular magnitude and in a very particular direction to produce this result. Too much acceleration, and 3i Atlas would have been deflected onto a path that missed Jupiter's Hill radius by a wide margin. Too little, and the same problem. A different direction of thrust, and again, the result would be completely different. But somehow the outgassing that occurred produced exactly the right velocity change to aim 3i Atlas at Jupiter's gravitational boundary. Several researchers immediately began calculating the probability of this occurring by chance. They ran Monte Carlo simulations generating thousands of hypothetical outgassing scenarios with random magnitudes and directions, and checking how many of them would produce trajectories that pass within a small distance, tolerance of Jupiter's Hill radius. The results showed extremely low probability, not impossible, but highly improbable. The kind of coincidence that makes you look twice at the data to make sure you haven't made a calculation error. But the data was solid. Multiple independent groups verified the trajectory calculations. The observations were consistent across different telescopes and different observation methods. There was no mistake. 3i Atlas really did undergo a trajectory change at Perihelion that redirected it toward Jupiter's Hill radius with remarkable precision. The question that naturally arose was, is this purely coincidental, or is there something we're not understanding about the physics involved? Some scientists argued for the coincidence explanation. Space is full of unlikely events, they pointed out. With billions of comets throughout the galaxy, occasionally one of them will experience an outgassing event that produces an apparently meaningful trajectory. We're only noticing this one because it happens to be passing through our solar system, where we can observe it. If there were thousands of interstellar comets being tracked simultaneously, we'd probably see all sorts of seemingly improbable trajectories, and this wouldn't look special. It's a selection effect, they argued. We're paying attention to the rare cases because they're rare, not because they're physically significant. Others weren't convinced by this reasoning. They pointed out that the margin of accuracy here was extremely tight, much tighter than you'd expect from random outgassing. They noted that the timing of the outburst, right at perihelion when solar heating was maximum, seemed almost optimized to produce a trajectory change at the point where it would be most effective. They questioned whether natural outgassing could really be this precise, without some mechanism that we don't yet understand causing it to preferentially occur in directions that lead to specific outcomes. And then there were the researchers who suggested something more controversial, that perhaps the non-gravitational acceleration wasn't entirely natural, that perhaps 3I Atlas represented something other than a simple comet, that perhaps the precision involved indicated intentional course correction rather than random outgassing. These voices were careful to frame their suggestions as hypotheses rather than conclusions, and they acknowledged the extraordinary claims required extraordinary evidence. But they argued that dismissing the possibility without investigation would be unscientific. If the trajectory really was as precise as the data suggested, they said, then all explanations, including unconventional ones, deserved consideration. This debate was still ongoing when the final trajectory refinements came in earlier this year, confirming beyond any reasonable doubt that 3I Atlas would reach Jupiter's Hill radius in March. And that confirmation meant that the mystery would soon have a resolution, because unlike previous interstellar visitors that came and went before we could study them thoroughly, this time we would have spacecraft in position to observe what happens next. This time we could gather real-time data during the encounter itself. This time we would get answers, not just speculation. But before we explore what those spacecraft might observe, we need to understand just how precise this targeting really is, and why the precision itself is the most puzzling aspect of the entire situation. Let's talk about numbers for a moment, because the precision involved here is what separates an interesting, astronomical event from a genuine mystery. When scientists say 3I Atlas is targeting Jupiter's Hill radius, they're not speaking metaphorically. They mean the trajectory calculations show an arrival at a distance that matches the Hill radius to an extraordinary degree of accuracy. And when you understand exactly how accurate we're talking about, the coincidence becomes much harder to dismiss casually. Jupiter's Hill radius, as calculated from its mass and orbital distance from the Sun, is approximately 53.5 million kilometers. This is a mathematical result derived from well-established equations in celestial mechanics. It's not an estimate or an approximation, it's a precise number that defines the distance at which Jupiter's gravitational influence equals the Sun's influence for an object in that region of space. Now, according to the latest trajectory calculations from NASA's Jet Propulsion Laboratory, and confirmed by other institutions, 3I Atlas will make its closest approach to Jupiter on March 16th, at a distance of 53.4 million kilometers. The difference between these two numbers is less than 100,000 kilometers. That's less than 0.2%. In the context of interplanetary distances, where we routinely deal with millions and tens of millions of kilometers, this is astonishingly precise. It's comparable to throwing a dart from one city and hitting a target in another city hundreds of miles away. The scale of accuracy here isn't something you expect from random natural processes acting on an object that travelled through interstellar space for an unknown duration before entering our solar system. To put this in perspective, consider what had to happen for this precision to occur. 3I Atlas originated somewhere in the galaxy, possibly ejected from its home star system through gravitational interactions, possibly released from a star cluster, possibly part of a population of rogue objects drifting through interstellar space. During its journey to our solar system, it would have been influenced by the collective gravitational field of the Milky Way, by random encounters with molecular clouds, by the accumulated effects of passing near other stars. All of these influences shaped its trajectory long before it arrived here. When 3I Atlas entered our solar system, it was moving on some trajectory determined by all that prior history. As it approached the Sun's gravity bent its path according to completely predictable physics. Astronomers could calculate exactly where it would go based on its velocity and position, and those calculations showed it would swing past the Sun and exit the solar system without any particularly close planetary encounters. This was the natural trajectory, the path determined by gravity alone. Then came the outgassing event at Perihelion. This introduced a non-gravitational force, essentially a random push from the comet's own activity. Outgassing is a chaotic process. It depends on which parts of the nucleus are facing the Sun, what the internal structure of the nucleus looks like, where pockets of volatile material are located, how cracks and vents in the surface allow gas to escape. There's no reason to expect outgassing to push a comet in any particular direction. It's essentially random from the perspective of producing a specific future trajectory, and yet, the outgassing that occurred on 3I Atlas pushed it in exactly the direction, with exactly the magnitude needed to redirect its path toward Jupiter's Hill radius. Not toward Jupiter itself, which would be easier to explain as a gravitational focusing effect, not to some random distance from Jupiter, to the specific threshold distance that represents Jupiter's gravitational boundary. The odds of this happening by pure chance are, according to several statistical analyses, somewhere in the range of 1 in several thousand to 1 in tens of thousands, depending on how you define the acceptable margin of error. Now, 1 in 10,000 isn't impossible. If there are tens of thousands of interstellar comets passing through the galaxy, you'd expect to occasionally see one that does something improbable. This is the argument that many scientists make when discussing 3I Atlas. They point out that improbable events happen all the time if you look at enough cases. Someone wins the lottery despite terrible odds, because millions of people buy tickets. We're just seeing the one interstellar comet that happened to have the right trajectory, and we're ascribing significance to it because we're the observers. But there's a counter-argument to this, and it's worth considering seriously. The counter-argument is that we're not actually observing tens of thousands of interstellar comets. We've only confirmed 3 interstellar objects passing through our solar system ever. The first was Oumuamua, which caused controversy because of its unusual acceleration and elongated shape. The second was 2I Borisov, which behaved like a normal comet and didn't raise any particular concerns. And now we have 3I Atlas, which is displaying this extraordinary targeting precision. That's not a large sample size. That's not enough cases to invoke the law of large numbers and say, improbable things are expected to occasionally happen. In fact, if you think about it, having 1 out of 3 interstellar objects display highly unusual characteristics that provoke scientific debate about whether they're natural is a surprisingly high ratio. 33% is not a small percentage. If interstellar objects were just random chunks of ice and rock with nothing special about them, you'd expect them all to behave predictably. The fact that we're already seeing anomalies in this tiny sample is, to some researchers, more concerning than reassuring. There's another aspect of the precision that makes it harder to explain as coincidence. It's not just that 3I Atlas is reaching the Hill radius, it's that the approach is happening at an optimal time in Jupiter's orbit, and from a direction that maximizes the observational opportunity. The geometry of the encounter is such that spacecraft near Jupiter will have excellent viewing angles. Ground-based telescopes on Earth will be able to observe the approach and the aftermath. The timing coincides with a period when Jupiter is relatively well positioned in the sky for Northern Hemisphere observatories. All of these factors combine to create an almost ideal observational scenario. Again, you can argue this is coincidence. You can say that we're only noticing these favourable conditions because they exist, and if the timing were different or the geometry worse, we'd be complaining about not having good observations. This is a valid point. But it adds another layer of improbability to stack on top of the trajectory precision. Each individually unlikely factor might be dismissible, but when you combine them, the trajectory targeting the Hill radius, the timing of the encounter, the favourable observational geometry, the cumulative probability becomes increasingly difficult to attribute to pure chance. This is where the scientific debate becomes genuinely interesting, because you have researchers looking at the same data and reaching different conclusions based on their prior assumptions about what's possible. If you start with the assumption that interstellar objects are just natural comets and asteroids, then you're forced to conclude that 3I Atlas represents an improbable, but ultimately meaningless coincidence. The precision must be random because there's no natural mechanism that could produce intentional targeting, and non-natural explanations are beyond consideration. But if you start with the assumption that our understanding of interstellar objects is incomplete, that we've only observed a handful of them, and therefore might be missing important characteristics of their behaviour, then the precision becomes a clue rather than a coincidence. It suggests that maybe there's something about how interstellar objects interact with planetary systems that we haven't discovered yet. Maybe there are natural mechanisms, some kind of gravitational focusing effect or plasma interactions in the solar wind, or something else entirely, that cause these objects to preferentially approach planets at specific distances. This would be new physics, or at least new applications of known physics in contexts we haven't studied before. And then there's the third perspective, the one that generates the most controversy, but that a small number of credible scientists have been willing to voice publicly. This perspective suggests that if the precision really is as extraordinary as it appears, and if no plausible natural mechanism can be identified that would produce this outcome, then perhaps we should consider the possibility that 3i Atlas isn't entirely natural. Perhaps it represents some form of technology, either currently active or remnant, that's capable of course correction. Perhaps the outgassing wasn't random but was directed in some way. Perhaps what we're calling a comet is actually something more complex. This is an extraordinarily controversial suggestion, and I want to be very clear about something. There is currently no definitive evidence that 3i Atlas is anything other than a natural comet. The spectroscopic analysis shows a composition consistent with cometary material. The outgassing appears to be standard sublimation of volatile ices. Nothing about its physical characteristics necessarily suggests artificial origin. The only thing that's unusual is the trajectory, and unusual trajectories alone are not proof of anything. However, what several researchers have pointed out is that the trajectory is unusual enough to warrant serious investigation rather than casual dismissal. They argue that science advances by examining anomalies, not by explaining them away. When something doesn't fit our models, when something displays characteristics that are statistically improbable, that's exactly when we should look more carefully, gather more data, and consider whether our models might be incomplete. This is precisely what's going to happen in March. We're going to get that additional data. We're going to observe 3i Atlas as it passes through Jupiter's Hill radius, and we're going to see whether anything unusual occurs. Does it maintain its trajectory exactly as gravitational models predict? Does it experience perturbations that can be fully explained by Jupiter's gravitational field? Does it display any characteristics, changes in brightness, alterations in outgassing patterns, trajectory adjustments, anything at all, that deviate from expected cometary behavior? The precision problem ultimately will be resolved not through debate but through observation. Either the March encounter will reveal natural explanations for everything we've been seeing, in which case 3i Atlas will go down in history as a fascinating but ultimately explainable case of cosmic coincidence, or the encounter will reveal additional anomalies that deepen the mystery and force us to expand our understanding of what's possible. Both outcomes would be scientifically valuable. Both would teach us something important. But only one of them would challenge our fundamental assumptions about what kinds of objects travel between the stars. To understand what might happen during that encounter, we need to explore the physics of gravitational perturbation and what occurs when any object crosses the threshold of a planet's Hill radius, because the effects can be dramatic and revealing. When an object crosses into Jupiter's Hill radius, it enters a different gravitational regime. The physics that governs its motion shifts from solar-dominated to Jupiter-dominated, and this transition can produce profound effects on the object's trajectory. To understand what might happen to 3i Atlas in March, we need to understand gravitational perturbation, the way that planetary encounters alter the paths of comets and asteroids in predictable yet often dramatic ways. Imagine you're rolling a ball across a flat surface, and suddenly there's a depression in that surface, a gravitational well that the ball approaches. As the ball gets closer to the well, it starts to curve toward it, accelerating as it descends. If the ball is moving fast enough, it might swing around the bottom of the well and come back out the other side. But its direction will have changed. Its speed might have changed too, either faster or slower depending on the geometry of the encounter. This is essentially what happens when a comet encounters a planet like Jupiter. The Hill radius represents the edge of that gravitational well, the distance at which the depression in the gravitational landscape becomes dominated by Jupiter rather than the Sun. Cross that boundary, and Jupiter's gravity begins to significantly alter the object's motion. The closer the object gets to Jupiter, the stronger the effect becomes, until at some point the perturbation is so extreme that the object's entire orbital destiny is rewritten. We've seen this happen many times with solar system comets. Some of them approach Jupiter and get captured into orbits that bring them back repeatedly, becoming what we call Jupiter family comets. Their orbital periods shrink from thousands of years to just a few years because Jupiter's gravity has trapped them into tighter, faster orbits. Other comets approach Jupiter and get accelerated, gaining enough velocity to escape the solar system entirely. Jupiter essentially flings them outward at speeds high enough to overcome the Sun's gravitational pull, ejecting them into interstellar space. The outcome depends on the geometry of the encounter, the approach velocity, the angle, the closest distance. A comet that passes in front of Jupiter in its orbit, what's called a prograde encounter, will be accelerated and might be ejected. A comet that passes behind Jupiter in its orbit, a retrograde encounter, will be decelerated and might be captured. These gravitational assists, as they're called in spacecraft navigation, are powerful tools for changing trajectories with minimal energy expenditure. We use them deliberately for space missions, carefully planning encounters with planets to bend spacecraft trajectories in desired directions. For 3i Atlas, approaching Jupiter at the Hill radius distance represents a moderate perturbation scenario. It's not going to plunge deep into Jupiter's gravitational well. It's not going to have a close encounter measured in terms of Jupiter radii, where tidal forces might tear it apart, or where the gravity would produce extreme trajectory changes. Instead, it's going to skim along the boundary region where Jupiter's influence transitions from dominant to subordinate. The perturbation will be measurable but not catastrophic. What we expect to see, based purely on gravitational calculations, is a bending of 3i Atlas's trajectory as it passes near Jupiter. The exact amount of bending depends on the geometry, which is well characterized at this point. Scientists have run the simulations. They know approximately how much Jupiter's gravity should deflect the comet's path. They know what the exit trajectory should look like after the encounter. These predictions are testable. When March arrives, we'll be able to compare what actually happens to what the models predicted, and any deviation from prediction would be significant. The other effect we'll observe is velocity change. As 3i Atlas swings past Jupiter, it will exchange momentum with the planet through gravitational interaction. Because Jupiter is vastly more massive than the comet, Jupiter's orbit won't change measurably, but the comet's velocity will. Depending on the encounter geometry, 3i Atlas will either be accelerated or decelerated. This will determine whether its post-encounter trajectory remains hyperbolic, keeping it on a path that will eventually leave the solar system, or becomes elliptical, trapping it in a bound orbit around the Sun. Current predictions suggest 3i Atlas will remain hyperbolic, meaning it will still be moving fast enough after the Jupiter encounter to eventually escape the solar system. But the trajectory will be different from what it would have been without Jupiter's perturbation. The direction will change. The timing of when it leaves the solar system will change. Everything about its future path is being determined by this encounter. Now, here's what makes this scientifically valuable. We've never before observed an interstellar object experiencing a close planetary encounter with this level of preparation and instrumental capability. When Oumuamua passed through the solar system, we detected it too late. It was already leaving by the time we realized what it was. We couldn't position spacecraft to observe it. We couldn't gather detailed data during any planetary encounters. With 2i Borisov, we had more advance warning, but it didn't have any close encounters with major planets. It passed through the solar system along a trajectory that kept it relatively isolated from strong planetary perturbations. 3i Atlas is different. We know it's coming, we know exactly where it's going. We have months to prepare observations, and we have spacecraft near Jupiter that can turn their instruments toward this visitor and record data during the encounter itself. This is an unprecedented opportunity to study how Jupiter's gravity affects an interstellar object, to compare its behavior to what we've learned from solar system comets, and to test whether objects from other stellar systems respond to gravitational perturbations exactly the way our local population does. That last point is important because there's no guarantee that interstellar comets are identical to solar system comets. They formed in different environments, they spent billions of years in different conditions. Their compositions might be subtly different in ways that affect how they respond to gravitational and thermal stress. By observing 3i Atlas during this Jupiter encounter, we can characterize its physical properties more precisely than would otherwise be possible. We can measure how its rotation changes under Jupiter's tidal influence. We can watch for outgassing variations as the gravitational environment shifts. We can build a complete profile of how an interstellar visitor behaves during a major planetary encounter. But there's another reason this observation is crucial, and it relates directly to the precision mystery we've been discussing. If 3i Atlas displays any behavior during the Jupiter encounter that deviates from purely gravitational predictions, that deviation would be extraordinarily significant. If it experiences additional non-gravitational acceleration during the passage, if its trajectory changes in ways that can't be explained by Jupiter's gravity alone, if anything unusual happens that suggests active processes beyond standard cometary outgassing, then the questions about this object's nature would intensify dramatically. This is why the March observation period is so important. It's not just about watching a comet pass a planet. It's about testing whether everything we're seeing can be explained by the physics we understand, or whether we need to expand our framework for understanding what's possible. And the gravitational perturbation effects themselves will serve as a diagnostic tool, allowing us to measure properties of 3I Atlas that would otherwise remain hidden. The history of planetary science is filled with examples of unexpected discoveries made during close encounters. We've learned about moon systems we didn't know existed. We've discovered rings around planets that appeared ringless from a distance. We've detected magnetic fields, measured atmospheric compositions, and observed geological activity that completely surprised us. Every time we get a close look at something we've only seen from afar, we learn something new. The Jupiter 3I Atlas encounter will be no different. So as we approach March, the gravitational perturbation that 3I Atlas will experience serves two purposes. First, it's a natural phenomenon that will teach us about how interstellar objects interact with major planets. Second, it's a test that will either confirm our understanding of this object or reveal that something more complex is happening. Either way, the data we collect will be valuable. Either way, we'll learn something important about the nature of objects that travel between stars and occasionally pass through our cosmic neighbourhood. But what about those controversial theories we mentioned earlier? The suggestions that perhaps 3I Atlas represents something other than a simple comet? We need to address those theories directly and examine what evidence supports or contradicts them, because they're part of the conversation whether we're comfortable with that or not. There's a conversation happening in certain corners of the astronomical community that makes many scientists uncomfortable, and it centres on whether 3I Atlas might represent something beyond a natural comet. This is controversial territory, and I want to be extremely clear about something before we go any further. Speculation is not evidence, and controversial hypotheses are not conclusions. What we're about to discuss represents theories that have been proposed by credentialed researchers, but that remain unverified and in many cases unfalsifiable with current data. These are ideas worth examining not because they're proven, but because they're part of the scientific process of considering all possible explanations for observed phenomena. The most prominent voice suggesting non-natural explanations for unusual interstellar objects has been Avi Loeb, a Harvard astrophysicist who chairs the astronomy department there. Loeb gained significant attention and criticism for his hypothesis that Oumuamua, the first detected interstellar object, might have been artificial in origin. His reasoning was based on Oumuamua's unusual acceleration, its elongated shape, and its trajectory characteristics that didn't quite match what you'd expect from a natural comet or asteroid. Many scientists disagreed with his interpretation, proposing alternative natural explanations for Oumuamua's properties. But Loeb argued that dismissing the possibility of artificial objects travelling through interstellar space was itself unscientific, that we should be open to considering evidence-based hypotheses even if they challenge conventional assumptions. When 3I Atlas began showing its unusual trajectory precision toward Jupiter's Hill radius, Loeb was among the first to publicly suggest that the object warranted careful scrutiny. In published commentary and interviews, he pointed out that the non-gravitational acceleration observed at Perihelion appeared to be finely tuned to produce a specific outcome, the Jupiter encounter, with precision that seemed anomalous for random outgassing. He suggested that one hypothesis worth considering was that the outgassing wasn't entirely random, that perhaps it represented a controlled thrust event designed to adjust the trajectory. Now, to be clear, Loeb hasn't claimed definitively that 3I Atlas is artificial. What he's argued is that we shouldn't automatically dismiss the possibility without investigation. He's called for more detailed observations, for spectroscopic analysis to search for any unusual materials or signatures that wouldn't be present in natural comets, and for careful monitoring during the Jupiter encounter to see if any additional anomalies appear. His position is essentially that extraordinary precision warrants extraordinary scrutiny. Other researchers have proposed variations on this theme. Some have suggested that if 3I Atlas were a probe of some kind, either currently active or a remnant from some previous civilization, the Jupiter encounter could be intentional. Jupiter represents a scientifically interesting target for any entity exploring stellar systems. It's the dominant planet, it has a complex satellite system, it has powerful magnetosphere and radiation belts. A probe designed to survey our solar system would naturally be interested in Jupiter. The fact that 3I Atlas is approaching Jupiter's Hill radius specifically, rather than making a random passage at some arbitrary distance, could indicate deliberate targeting for scientific observation of Jupiter's gravitational environment. This is extremely speculative, and most astronomers reject these interpretations. Their objections are reasonable and worth considering. First, They point out that there's no physical evidence of artificial materials or structures on 3i Atlas. The spectroscopic data shows water ice, carbon monoxide, dust, all materials consistent with natural comets. There's no detection of metals, synthetic compounds, or anything you'd associate with manufactured objects. Second, the outgassing behaviour, while coincidentally well-directed, follows patterns consistent with natural sublimation. There's no indication of exhaust plumes or directed thrust that you'd expect from a propulsion system. Third, the object's behaviour throughout its passage has been entirely consistent with a comet responding to solar heating and gravitational forces. Nothing has occurred that requires invoking non-natural explanations. The mainstream scientific position is that 3i Atlas is a comet, that the trajectory precision is coincidental, and that the Jupiter encounter will confirm this through observations showing purely gravitational perturbation effects with no anomalies. This position is supported by the fact that, despite initial concerns about Oumuamua, subsequent analysis has provided increasingly plausible natural explanations for its unusual characteristics. The scientific community has learned from that experience to be cautious about jumping to extraordinary conclusions based on limited data. However, there's a middle ground perspective that's worth considering. This perspective acknowledges that 3i Atlas is most likely natural, but argues that our sample size of observed interstellar objects is too small to make definitive statements about what's normal for this population. We've only seen 3 confirmed interstellar visitors. We don't know what the full range of behaviours and characteristics is for objects travelling between stars. It's entirely possible that interstellar comets behave somewhat differently from solar system comets, in ways we haven't yet characterised. Perhaps their compositions include volatiles that sublime at different rates or temperatures. Perhaps their internal structures, formed in different protoplanetary environments, lead to different outgassing patterns. Perhaps there are natural mechanisms we haven't discovered that cause certain trajectory outcomes to be more common than random chance would suggest. This middle ground view suggests that the unusual precision of 3i Atlas's trajectory could be telling us something important about interstellar object physics, without necessarily indicating artificial origin. It could be highlighting a gap in our understanding rather than evidence of technology, and this is actually the position that many researchers who are intrigued by the 3i Atlas case take. They're not convinced it's artificial, but they are convinced it's worthy of serious study because it might teach us something new about natural processes we haven't fully understood. There's also been discussion about what we should look for during the March encounter if we're serious about investigating whether 3i Atlas displays any unusual characteristics. Several researchers have published lists of potential anomalies that would be significant if detected. These include unexpected trajectory changes during the Jupiter passage that can't be explained by gravitational perturbation alone. They include unusual outgassing patterns or brightness variations that don't correlate with solar heating and distance. They include any spectroscopic signatures that deviate from expected cometary composition. They include variations in rotation rate or orientation that suggest active stabilization rather than passive tumbling. The idea behind creating such lists is to have clear criteria established in advance for what would constitute genuinely anomalous behavior versus what would be consistent with natural cometary activity. This kind of structured approach is how science operates. You define your predictions, you collect data, you compare results to predictions, and you draw conclusions based on whether the observations matched expectations. If everything behaves exactly as gravitational models predict, then 3i Atlas is a comet, and the trajectory precision was coincidental. If deviations appear that require additional explanations beyond gravity and standard outgassing, then the mystery deepens and further investigation is warranted. One theory that's been proposed, which falls somewhere between purely natural and artificial, is that 3i Atlas could be a defunct spacecraft or probe that's no longer actively controlled, but that retains structural features that affect how it responds to solar heating. Imagine an object that was manufactured long ago, possibly millions of years ago, that has spent eons drifting through space accumulating ice and dust on its surface. From a distance it might appear identical to a natural comet. Its spectrum might show cometary materials because those materials are what's coating its exterior. But underneath that natural accumulation could be a manufactured core that affects the object's mass distribution, rotation, and outgassing behaviour in subtle ways. This idea is almost unfalsifiable with current observational capabilities, which is one reason it remains speculative. We can't resolve the surface of 3i Atlas in enough detail to see whether there are structural features inconsistent with natural formation. We can't land on it or take samples. We can only observe it from a distance and analyze the light it reflects and emits. That limited data stream makes it very difficult to definitively rule out scenarios like this, but it also makes it impossible to confirm them. Without extraordinary evidence, something that clearly cannot be natural, the scientific default position is to assume the natural explanation until proven otherwise. What makes the 3i Atlas case different from typical fringe claims about anomalous objects is that the scientists discussing these possibilities aren't conspiracy theorists or pseudoscience promoters. They're published researchers with legitimate credentials who are approaching this from a scientific perspective. They're not claiming certainty about unconventional explanations. They're arguing for keeping an open mind and collecting more data before closing the case. There's a difference between saying this is definitely artificial and saying this is unusual enough that we should investigate carefully, rather than assuming we already understand it completely. The counterpoint to this, which the skeptical majority of astronomers emphasize, is that keeping an open mind doesn't mean giving equal weight to all possibilities. Natural explanations should be preferred until they're conclusively ruled out, because natural explanations are consistent with everything else we know about the universe, while artificial explanations require adding entirely new assumptions about the existence of other technological civilizations and their activities. This principle, often called Occam's razor, suggests that the simplest explanation consistent with the evidence is most likely correct. Since a natural comet with coincidentally precise trajectory is simpler than an artificial probe from an unknown civilization, the natural explanation should be our working hypothesis until it fails to account for observations. Both sides of this debate have valid points. Yes, we should prefer natural explanations and not jump to extraordinary conclusions prematurely, but also yes, we should remain genuinely open to evidence that might challenge our assumptions and should design our observations to test competing hypotheses rather than simply confirming what we already believe. The best outcome would be observations that definitively answer the question, that provide such clear evidence in one direction or the other that the debate is resolved. Whether we'll get that level of clarity from the March encounter remains to be seen. What we can say with confidence is that 3i Atlas has generated more scientific discussion and attention than a typical comet would, precisely because of these unresolved questions about its trajectory. Whether that attention is warranted or whether it represents overthinking a coincidence, we'll know more in a few months. The data will speak for itself. The observations will either show a comet behaving exactly as expected, or they'll show something that requires further explanation. Until then, the speculative theories remain exactly that. Speculation based on incomplete information, worthy of consideration but not worthy of acceptance as established fact. The reality is that science advances through this kind of tension between conservative interpretation and openness to new possibilities. Too much conservatism leads to missed discoveries when something genuinely unusual appears. Too much openness leads to wasted effort chasing phenomena that turn out to have mundane explanations. The balance is in collecting rigorous data and letting that data guide conclusions rather than letting preconceptions, either conventional or unconventional, determine what we see. And that brings us to perhaps the most exciting aspect of this entire situation. We have spacecraft in position to observe this encounter closely, and those observations will provide data far more detailed than anything we could obtain from ground-based telescopes alone. March is going to be a busy month for the spacecraft currently operating near Jupiter. When 3i Atlas makes its closest approach on March 16th, multiple instruments on multiple missions will be tracking this interstellar visitor as it passes through Jupiter's Hill radius, collecting data that will either solve the trajectory precision mystery or deepen it considerably. This is what makes the upcoming encounter so scientifically valuable. We're not just watching from Earth, we're observing from positions throughout the Jovian system, with instruments specifically designed to study comets and planetary environments. The primary observer will be NASA's Juno spacecraft, which has been orbiting Jupiter since 2016. Juno's mission has been to study Jupiter's atmosphere, magnetosphere, and interior structure, but its instruments are also capable of observing distant objects like comets when opportunities arise. Juno carries a camera called Juno Cam that produces stunning visible light images of Jupiter's clouds. and while JunoCam isn't optimized for faint object detection, it can be pointed toward 3i Atlas during the encounter to capture images showing the comet's position relative to Jupiter. More importantly, Juno carries instruments that measure magnetic fields, plasma environment, and energetic particles, all of which could detect interactions between Jupiter's magnetosphere and any material being released by 3i Atlas as it passes nearby. Juno's orbit around Jupiter is highly elliptical, bringing it close to the planet during each perihelion pass, and then swinging out to much greater distances during aphelion. Depending on where Juno is in its orbit during the March encounter, it might be relatively close to 3i Atlas's flight path, or it might be on the opposite side of Jupiter. NASA has time to plan Juno's observation strategy, potentially adjusting the timing of instrument operations to maximize the scientific return from this encounter. The data Juno collects will be particularly valuable for understanding whether 3i Atlas interacts with Jupiter's magnetic field in unusual ways, which could indicate unexpected plasma emission from the comet or anomalous electrical properties. The European Space Agency's JUICE spacecraft, which stands for Jupiter Icy Moons Explorer, is also in the vicinity, though its position relative to 3i Atlas during the encounter will depend on its trajectory following its launch. JUICE is designed to study Jupiter's moons, particularly Ganymede, Europa, and Callisto, but like Juno, it carries instruments that can observe distant objects. If JUICE is positioned favourably, its cameras and spectrometers could capture data on 3i Atlas's composition and activity level during the crucial passage through Jupiter's Hill radius. NASA's Europa Clipper mission, depending on its launch timing and cruise trajectory, may also be in a position to contribute observations, though this mission is primarily focused on Europa and its subsurface ocean. These spacecraft represent an unprecedented observational capability that didn't exist during previous interstellar object encounters. When Oumuamua passed through, we had no spacecraft near any of its closest approach points. When Borisov came through, the geometry didn't favour spacecraft observations, but for 3i Atlas, we have assets in place. Ground-based observations will supplement the spacecraft data. Major observatories around the world are preparing observation campaigns for March, coordinating telescope time to ensure continuous coverage of 3i Atlas during the critical period. The Hubble Space Telescope, despite being an aging instrument, can still capture high-resolution images of comets and will likely be pointed toward 3i Atlas to document its appearance before and after the Jupiter encounter. The James Webb Space Telescope, with its infrared capabilities, can detect heat signatures and compositional details that visible light telescopes miss. These observations will provide crucial context for interpreting the spacecraft data. What exactly will all these instruments be looking for? The primary objective is to track 3i Atlas's trajectory with extreme precision throughout the encounter. Any deviation from predicted gravitational perturbation would be significant. If the comet's path bends exactly as Jupiter's gravity should bend it, that supports the natural explanation. If additional trajectory changes occur that can't be attributed to gravity, that would require explanation. The spacecraft near Jupiter are positioned to measure these trajectory changes with far greater accuracy than ground-based observations alone could achieve, because they can determine the comet's position relative to Jupiter directly rather than inferring it from observations made from Earth. The second major observation goal is to monitor 3i Atlas's activity level. Is the comet outgassing as it approaches Jupiter? Is it brightening due to increased activity? Comets often respond to changing gravitational environments with altered outgassing behaviour, and any such changes in 3i Atlas would be important to document. If the comet remains relatively inactive during the encounter, that would be unusual and potentially significant. If it displays outgassing patterns that correlate with its position relative to Jupiter's Hill radius, that could provide clues about what physical processes are affecting it. Spectroscopic analysis during the encounter will be crucial for characterizing 3i Atlas's composition in detail. By analyzing the light reflected and emitted by the comet, spectrometers can identify specific molecules in its coma and tail. If the composition changes during the Jupiter encounter, if new materials appear, or if the ratios of different compounds shift, that information would help us understand what's happening physically to the comet as it experiences Jupiter's gravitational influence. Any unexpected materials or spectral features that don't match typical cometary composition would be scientifically significant and potentially controversial. Another important measurement will be rotation. Comets typically tumble in space, rotating at rates determined by their formation history, and any subsequent collisions or outgassing events that imparted angular momentum. If 3I Atlas's rotation changes during the Jupiter encounter in ways that are consistent with tidal torques from Jupiter's gravity, that's expected behaviour. If the rotation changes in unexpected ways, or if the comet appears to be rotating more stably than random tumbling would suggest, that could indicate internal mass distribution that's unusual for a natural object. Spacecraft observations, particularly if Juno gets multiple viewing angles over time, can help characterize the comet's rotation and look for any anomalies. The observation window isn't just the day of closest approach. Scientists will be tracking 3I Atlas for weeks before and after March 16th to document the full arc of the encounter. The pre-encounter observations establish the baseline, what the comet looks like and how it's behaving before Jupiter's influence becomes dominant. The encounter observations capture what happens at the critical moment. The post-encounter observations document the aftermath, how the comet's trajectory changed, whether it was perturbed into a different orbit, whether its activity level increased or decreased, whether anything about its physical state was altered by the gravitational interaction. All of this data will be processed, analysed, and compared to models. Research teams will simulate the encounter using sophisticated gravitational physics software, predicting exactly how Jupiter should affect 3I Atlas based on the comet's known mass, position, and velocity. They'll compare those predictions to what was actually observed. If the observations match the predictions within expected margins of error, that strongly supports the natural explanation for everything we've seen. The trajectory precision was coincidental. The outgassing event at Perihelion happened to redirect the comet toward Jupiter's Hill radius by chance, and the encounter proceeds exactly as orbital mechanics dictates. But if the observations don't match predictions, if there are discrepancies that can't be explained by measurement uncertainty or model limitations, then the mystery deepens. Any such discrepancies would be scrutinized intensely. Alternative explanations would be developed and tested. Additional observations would be planned. The scientific process would continue, iterating toward better understanding through accumulation of evidence and refinement of theories. This is what makes the March encounter so important. It's a natural experiment, a test of our understanding, an opportunity to gather data that will either confirm what we think we know about interstellar objects, or reveal that we have more to learn. The fact that we have spacecraft positioned to observe it is extraordinarily fortunate. The fact that the encounter was predicted far enough in advance to allow careful planning and coordination is even more fortunate. We're going to get answers, or at least we're going to get data that moves us closer to answers, and regardless of what those answers turn out to be, regardless of whether 3I Atlas proves to be a completely natural comet with a coincidentally precise trajectory or something more puzzling, the observations themselves will be valuable. Every time we study an interstellar object, we learn something about the diversity of materials and structures that exist throughout the galaxy. We gain insights into how other stellar systems form planets and eject debris. We expand our catalogue of what's possible in the universe. That knowledge accumulation is the fundamental purpose of astronomy: to observe, to measure, to understand. So as March approaches, astronomers around the world are preparing. Observation schedules are being finalized, instrument calibrations are being checked, analysis software is being tested. Everything is being positioned to capture this encounter as thoroughly as possible. Because opportunities like this are rare, we might not see another interstellar object have a close encounter with a major planet for years or decades. When it happens, when 3I Atlas reaches Jupiter's Hill radius and all those instruments turn toward it, we'll be ready to observe whatever unfolds. And whatever we discover will add to our understanding of these mysterious visitors from beyond our solar system. But what would it actually mean if the observations confirm purely natural behaviour versus if they reveal something anomalous? What are the implications either way for our understanding of the universe? That's what we need to consider next. Let's think through what happens depending on what we observe in March. Because either outcome, whether 3I Atlas behaves exactly as expected or displays anomalies, would tell us something important. This isn't a situation where only one result would be scientifically valuable. Both possibilities advance our knowledge, just in different directions. Understanding what each scenario would mean helps us appreciate why this encounter matters, regardless of whether it resolves the precision mystery or deepens it. If the observations show that 3I Atlas behaves exactly as gravitational models predict, if its trajectory through Jupiter's Hill radius follows purely Newtonian physics with no anomalies, and if its physical characteristics remain consistent with natural cometary composition throughout the encounter, then we'll have confirmed something significant, that interstellar comets, at least this one, respond to planetary encounters in the same ways that solar system comets do. This might sound obvious, but it's not. We don't actually know yet whether objects formed in other stellar systems behave identically to objects formed in ours. Different stars have different compositions. They contain different ratios of elements depending on when they formed and what materials were available in their regions of the galaxy. Planets that form around those stars and comets that form in those protoplanetary disks might have subtly different compositions as a result. Those compositional differences could lead to different physical properties, different strengths, different volatile content, different responses to heating and gravitational stress. By observing an interstellar comet during a major planetary encounter and confirming it behaves as expected, we validate that the physics we've learned from solar system objects applies universally, at least within the range of conditions we've sampled. The natural behavior outcome would also resolve the trajectory precision question in favor of coincidence. If everything about 3I Atlas's encounter with Jupiter is explainable through standard physics, then the fact that it arrived at Jupiter's Hill radius with such accuracy must be attributable to chance. Improbable things happen. Sometimes the dice roll in ways that look meaningful but aren't. This would be a reminder to scientists to be cautious about ascribing significance to anomalies that might simply be statistical flukes. It would reinforce the value of waiting for confirmatory evidence before accepting controversial interpretations of limited data. From a public communication perspective, confirming natural behavior would be the cleaner, simpler outcome. It would allow astronomers to present a coherent story. Interstellar comet enters our system, gets heated by the sun, outgasses in a way that coincidentally redirects it toward Jupiter, passes Jupiter exactly as gravity predicts, and exits the solar system. No mysteries, no controversies, just nature doing what nature does. This is actually what most scientists expect and hope to see, because it's consistent with everything we understand about how the universe works. But what if the observations show something else? What if there are anomalies that can't be easily explained by natural processes? This is where things become genuinely interesting from a scientific standpoint, because anomalies force us to expand our models. They reveal gaps in our understanding. They point toward phenomena we haven't fully characterized yet. If 3I Atlas displays unexpected behavior during the Jupiter encounter, the immediate question becomes, what natural mechanism could explain this? Perhaps there are aspects of cometary physics we don't fully understand. Perhaps the internal structure of interstellar comets is different from solar system comets, in ways that affect their outgassing patterns or their responses to gravitational stress. Perhaps there are sublimation processes that occur at temperatures or pressures we haven't studied in laboratory conditions. Perhaps electromagnetic interactions between comet plasma and planetary magnetospheres can produce small but measurable thrust effects that we haven't accounted for in our models. Any of these possibilities, if confirmed, would represent genuine advances in our understanding of small body physics. The more controversial possibility, of course, is that anomalous behavior could indicate non-natural origin. If 3I Atlas displays characteristics that truly cannot be explained by any plausible natural mechanism, if it shows evidence of directed thrust or structural features inconsistent with natural formation, then the conversation changes dramatically. This remains highly unlikely. Most scientists consider it extremely improbable, but the possibility cannot be completely dismissed if the evidence points that direction. What would be the implications if we discovered that an interstellar object passing through our solar system was artificial? The first implication would be that we're not alone, that technological civilizations exist elsewhere in the galaxy and have developed capabilities for interstellar travel, or at least for sending probes between star systems. This would be one of the most profound discoveries in human history. Fundamentally altering our understanding of our place in the universe, it would raise immediate questions: who sent it, when, from where, for what purpose? But we need to be very clear about the evidentiary threshold required for such a conclusion. Extraordinary claims require extraordinary evidence, Ambiguous anomalies are not sufficient. What would be required is unambiguous evidence of artificial structure or function, something that clearly and undeniably could not form naturally. We're talking about detection of manufactured materials, geometric structures too regular to be natural, emission of signals, active propulsion that can't be mistaken for outgassing. Without evidence at that level, the scientific community would correctly remain skeptical of non-natural interpretations. There's also a middle ground outcome we should consider. The observations might show behaviour that's anomalous enough to be puzzling, but not clear enough to be definitive. We might see trajectory deviations that are difficult to explain, but that could potentially result from processes we don't fully understand. We might detect compositional features that are unusual but not impossible for natural objects. This ambiguous outcome would be scientifically frustrating, because it wouldn't resolve the mystery, it would just shift the debate. Some researchers would interpret the ambiguities as supporting non-natural hypotheses. Others would argue that ambiguous data should be interpreted conservatively as natural until proven otherwise. Regardless of which outcome we see, the March encounter will advance our knowledge about interstellar objects. We'll have detailed observations of how such an object behaves during a planetary encounter. We'll have spectroscopic data characterizing its composition. We'll have trajectory measurements that either confirm our physics models or point to gaps in those models. This is how science progresses, through accumulation of observations, through testing of theories, through refinement of our understanding based on new evidence. There's also a practical implication here that's worth mentioning. If interstellar objects turn out to be common visitors to our solar system, we need to develop better detection and tracking capabilities. Right now, we've only confirmed 3 interstellar objects because our surveys aren't optimized to find them. They're faint, they're moving quickly, and they're easy to miss unless you're specifically looking in the right place at the right time. But if there are hundreds or thousands of these objects passing through every year, as some estimates suggest, then we should be finding them more regularly. Better detection would allow us to study a larger sample, which would help us understand whether 3i Atlas is typical or unusual compared to other interstellar visitors. The upcoming Vera Rubin Observatory, which will conduct the legacy survey of space and time, is expected to dramatically improve our ability to detect interstellar objects. It will survey the entire visible sky repeatedly, finding faint moving objects that current surveys miss. When that observatory comes online, we'll likely start detecting interstellar visitors much more frequently. Each detection will add to our database, helping us understand the population characteristics, composition distributions, trajectory patterns, and physical properties of objects travelling between stars. So the implications of the 3i Atlas encounter extend beyond this single object. We're learning about a class of objects, not just an individual. We're developing observational techniques and analysis methods that will apply to future discoveries. We're building the foundation for a better understanding of the interstellar medium and what travels through it. Whether 3i Atlas turns out to be entirely ordinary or genuinely unusual, it's contributing to that larger scientific project, and ultimately that's what makes this exciting. We're not just watching a comet pass a planet, we're participating in humanity's ongoing effort to understand the universe we inhabit. We're testing theories, gathering data, asking questions, and refining answers. That process doesn't end with the March encounter. It continues as long as we keep observing and learning. But March will be a significant milestone in that ongoing process, a moment when we get clear data about something we've been speculating about for months. A moment when questions start to get answered, even if those answers lead to new questions. As we count down toward that encounter, there's a sense of anticipation building in the astronomical community. March 16th is circled on calendars, observation schedules are set, instruments are being prepared, and everyone who's been following this story is wondering what we'll see when 3i Atlas reaches Jupiter. We're now just months away from one of the most anticipated astronomical observations in recent memory. March 16th, 2026. That's the date when 3i Atlas will pass through Jupiter's Hill radius, when all the preparation and planning will culminate in actual observation, when we'll finally get data that answers some of the questions we've been asking since this object's trajectory precision first became apparent. The countdown is real, the encounter is coming, and what we discover could reshape our understanding of interstellar visitors to our solar system. Think about the journey that 3i Atlas has taken to reach this point. It formed somewhere around another star, possibly billions of years ago, in a protoplanetary disk that no longer exists. Through some process, gravitational ejection, stellar encounter, cluster dynamics, something, it was sent on a trajectory that carried it away from its birth star into the vast emptiness between stars. For thousands or millions of years it drifted through the galaxy, a lonely wanderer in the cosmic dark, slowly travelling across light years of space at speeds we can barely achieve with our fastest spacecraft. Then, by chance, or by something else, its path brought it toward our Sun. As it entered the outer reaches of the solar system, it began to feel the Sun's gravitational pull, subtle at first, but growing stronger as the distance decreased. Its trajectory bent, curved by gravity into a path that would bring it close to the Sun. As it passed through the inner solar system, solar radiation heated its icy surface, causing that dramatic outgassing event at Perihelion that altered its future course. And now it's approaching Jupiter, aimed with remarkable precision at the gravitational boundary that defines where Jupiter's influence dominates. This is not a common occurrence. We don't see interstellar objects having close planetary encounters regularly. Most of the interstellar visitors we've detected followed trajectories that kept them relatively isolated from the major planets. They passed through, got heated by the Sun, and left without significantly interacting with anything. But 3i Atlas is different. It's going to experience the full force of Jupiter's gravitational perturbation. It's going to cross a threshold that will alter its path permanently, and we're going to watch it happen. The observations that will be collected in March are going to be analysed for years. Every image, every spectrum, every trajectory measurement will be scrutinised by research teams around the world. Papers will be published presenting different interpretations of the data. Conferences will host sessions where scientists debate what the observations mean. This is how astronomy works when something genuinely interesting happens. The community comes together to make sense of new information, to test competing theories, to build toward consensus understanding. But beyond the scientific community, there's broader public interest in this encounter. People who aren't astronomers, who don't follow space news regularly, are curious about 3i Atlas because of the questions it raises. The precision mystery has captured attention in a way that a typical comet discovery wouldn't. There's something compelling about the idea that we might be watching something we don't fully understand, that an object from beyond our solar system is doing something that challenges our assumptions about what's natural. Whether that perception is accurate or not, it reflects a deeper human fascination with the unknown, with the possibility that the universe contains surprises we haven't anticipated. So as March approaches, I want to encourage you to stay engaged with this story. Follow the updates as observations are released. Pay attention to what the spacecraft near Jupiter detect. Read the analyses that scientists publish. Think critically about the evidence and what it supports. Don't accept extraordinary claims without extraordinary evidence, but also don't dismiss genuine mysteries just because they're uncomfortable. The truth about 3i Atlas, whatever it turns out to be, will emerge from careful observation and rigorous analysis, not from predetermined assumptions. And when March 16th arrives, when 3i Atlas crosses that invisible boundary around Jupiter, remember that you're witnessing something historically significant. Humanity has never before observed an interstellar object during a close planetary encounter with this level of instrumental capability and preparation. We've never had spacecraft positioned to gather real-time data during such an event. We've never had the ability to test our theories about interstellar visitors against direct observation of their behaviour in gravitational environments we can model precisely. This is a first. This is the beginning of a new era in our study of objects that travel between stars. The data we collect won't just answer questions about 3i Atlas specifically, it will inform our understanding of all future interstellar objects we detect. It will help us develop better models for predicting their behaviour. It will guide us in designing missions to intercept and study these visitors more thoroughly. It will contribute to the broader project of understanding what exists in the galaxy beyond our small corner of it, what kinds of objects are out there wandering between the stars, and how they interact with planetary systems they encounter along the way. I'll be covering the March encounter here on this channel as it unfolds. When the first observations are released, when spacecraft send back their data, when scientists start presenting their initial analyses, I'll be here breaking it down, explaining what it means, discussing the implications. Make sure you're subscribed so you don't miss that coverage. Hit the notification bell so YouTube actually tells you when new videos are posted. This is a story that's going to develop over weeks and months, not all at once, and you'll want to follow along as the picture becomes clearer. This has been a journey from the initial detection of unusual trajectory precision through the analysis of the October transformation at Perihelion, into the debates about what the precision means and whether it indicates anything beyond natural processes. We've explored the physics of gravitational perturbation, we've examined the speculative theories that some researchers have proposed, and we've discussed what spacecraft will observe during the encounter. Now we wait. Now we watch. Now we prepare to learn whatever 3i Atlas has to teach us about the nature of interstellar visitors and the physics that governs their behaviour. The countdown is on. March is coming. And whatever we discover, whether it resolves the mystery cleanly or deepens it further, will be worth the wait. Because this is what exploration looks like. Not always dramatic, not always immediately satisfying, but always advancing our understanding step by step, observation by observation, discovery by discovery. We're explorers not of physical space but of knowledge space, pushing the boundaries of what we know about the universe we inhabit. And 3i Atlas is inviting us to take another step forward into that unknown territory. So stay curious, stay engaged, stay critical, but open-minded, and when March 16th arrives, when those observations start coming in, be ready to learn something new about the cosmos and our place within it. The universe is full of mysteries, and we're fortunate enough to be living at a time when we have the technology and knowledge to investigate some of them. 3i Atlas is one of those mysteries, and we're about to find out what it reveals. I'll see you in the next video, and until then, keep looking up.